MCV4U, section of the textbook 2.2, derivative of polynomial functions. If you're watching this video, you've got two things that you've already done. One should have been from homework probably last night or earlier anyway, is there was a page that was called Derivative Shortcuts Prerequisite Skills, where you're asked to do a bit of algebra and think about different ways to write algebraic expressions. So that's done. And you did an in-class investigation that was called Derivative Shortcut Investigation, where you were basically taking the derivatives of some things from first principles and then checking with classmates and see what they got. I'm going to take that up in this video and then do some examples. And this is, you know, this lesson is a lot like what the rest of the course is going to feel like, this idea of taking the derivative and doing stuff and applying the derivative. So if you haven't finished that, you need to stop the video and go away and do something else. Do one of these things first. But I'm going to continue on here. This was the investigation, and depending on what group you were thrown into, you were asked to do something from first principles. And the one I want to do, because it's interesting, is this one. And I'm going to take that one up real quick. It's the derivative of the power rule. So when I have the derivative of a polynomial function x to the exponent n, what do I have, or what do I do? And so this was, I was pretending that I had the group, I was in a group, and this was my example, and then I did that, and I got that. What you're supposed to find is right here. Let me just go through it line by line. So we wanted to prove that this is true, that if f at x equals x to the exponent n, then the derivative is n times x to the exponent n minus 1. And so what did we do? Well, we went from first principles, right? The derivative of any function is the limit as h approaches 0 of, there's the quotient expression, right? And where the function is just where the function is x to the exponent n, x plus h in for x, then I've got that expression. And remember that warm-up we did the other day where we factored some stuff, right? This is like x to the exponent n minus y to the exponent n. This is what we did the other day. Warm-up. Then if I factored this out, the first factor is x minus y, red minus black, x minus y, and then the rest is, well, that expression except for with x plus h's and x's in there. Well, what happens? Well, what happens is the x minus x makes this an h, and I can cancel with the bottom, and I get a smiley face. What's even better then, because I got no h on the bottom, I get this expression, and I substitute in h is 0, and what do I get? I get a whole bunch of x plus zeros, n to the x plus 0, n to the exponent, that should be 2, by the way, 2 there, times x, and so on, and all of these end up being x to the exponent n minus 1s. There's n of them all together, right? N of them all together, and all of them end up being x to the exponent n minus 1s, because h goes to 0, right? And so there I have it. Therefore, f prime at x equals nx to if, and notice there's all the proofs are in the text. And is this a proof? Absolutely. This is what from first principles means, is to do these sorts of proofs. And this was the last chapter, and it shows up here when we're doing the proofs for this. But pretty much we're almost done with first principles. We're going to do a few first principles when we first meet a new function, but pretty much we're just going to do these what I call shortcuts. And so that was, you're supposed to get this together and write down with your group members all of these things, and I'll show you my version. There it is. It's probably posted in the classroom, I bet you. If you remind me, I can post this in the classroom. But there it is. Pause if you like. And here's some examples. The Leibniz notation, by the way, is very similar, right? D, the derivative of some function with, and this was with respect to x. Don't get scared by this. It still is just another way to write the derivative. All right, now for the good stuff. The derivative rules. So it says apply the derivative rules to differentiate each function. The power rule. Well, the power rule is when I have like a polynomial term, the exponent just comes down, and then I subtract one off the exponent. It's just that easy. That's calculus. This step is taking the derivative of both sides. They almost immediately get a little more difficult because when I have a power on the bottom, it's not quite so easy. But if I rewrite first, I'm going to rewrite y as x. I could think of this as 1, although it doesn't matter. X to the exponent minus 4, because remember the minus 4 means it's on the bottom. Then what happens? When I take the derivative, right, y prime, I take the derivative, the number part goes in front, and then I subtract 1 off of the exponent. And if I want to tidy that derivative up at the end so that I get a positive exponent, it's going to be negative 4 over x to the exponent 5. These are all that you're going to see today we could have got from first principles, although they're nasty. Roots are scary. They're not that scary if you write it in the nice form. The exponent is 2, the root is 3, and then now I take the derivative. The exponent comes down. Maybe I'll use the Leibniz notation. The derivative of s with respect to t, see t is the independent variable there, take the derivative of this, the 2/3 comes down, and then I subtract 1 off of 2/3. Now don't get scared by the fractions here. You should be able to do that in your head, yeah? Okay, so negative exponent means for you to put it in the bottom, right? The t gets put into the bottom with a positive exponent, 1/3, and this can still be tidied up. This is just the cube root, isn't it? So this is 2/3 times 1 over the cube root of t, or if I wanted to multiply the fractions across, 2 over 3 cube root of t. Is this any nicer than this one? Well, that's debatable, but that would probably be what your textbook is showing. The constant and constant multiple rule. The derivative of a constant. Well, which rule was that? Go back. The derivative of a constant of 17, of 12, of pi, of negative 845. The derivative of a constant is 0. So this is 0. Dandy. Well, what about when there's a number here? Well, basically what we do is we take the derivative of just this chunk here and worry about the number part later. The number part can tag out front. That's what this constant multiple rule is. The constant can tag out front and just take the derivative of the term itself. So the derivative of x to the exponent 4, the 4 comes down. Let's multiply x to the exponent 3. Now we're not going to leave it like this, right? We do some fractions. 3 times 4 is 12 over 7 x cubed. And if you can do this in your head, and by the end of tonight you will be able to, can you skip that step and go straight there? Absolutely you can. Onwards and upwards. Example F already. Holy moly, example F. And I'm going to try and mix and match notations as much as I can, but it doesn't really matter. I'm going to do R prime here. Oh, hang on, actually, because this is on the bottom, I'm going to rewrite this. I'm going to rewrite it so it looks like something that's kind of familiar, right? We've got a constant, our variable, and then a power. So now I'm going to take the derivative. Constant gets written down. The exponent comes down, and subtract 1 off the exponent, and then tidy up. 4 times 2 times 9 minus 4 t negative 3. Well, let's tidy that up. Why not? There, dandy. This looks weird. Don't like having this part here, but well, rearrange it so it looks more nice for us. There's the constant part. That's like the k. And then x, what's the root? Well, that's a half. Exponent a half. All right, well, take the derivative. Maybe I'll use Leibniz notation. Why not? Switch things up, eh? dy, the dx, because x is the independent variable here. The half comes down. The k gets written out front. Now there's some weirdness going on here, but we're not worried about that yet. Then subtract that. Subtract 1 off of a half. A half subtract 1 is negative a half, right? And then I got to tidy this up. Well, negative a half is in the bottom, and the half is a root, so this is 2 root x. And that still looks pretty nasty. There's probably some more creative stuff that you could do here. For instance, and this is not for the faint of heart, so be careful here. Here's an aside. Right? We know that we got root 2, and 2 is actually root 2 squared, right? So if I wanted to write 2 as root 2 squared, and I'm just going to write that square root of x down there, well, what do I got? I got 1 on the top, 2 on the bottom. I could cancel 1 out, and I could write this as root 2 and root x. Oh, hang on. Geez, that's not that bad at all. So this, through our aside here, actually turns into 1 over the square root of 2x. Wow, wow, wow. That's not as awful as it looked early on. Maybe there's a shortcut to our shortcut, but that's for another story. I am going to stop there and pick up the rest of the examples in part 2.